With this unit, we are going to explore what happens when charges start moving and changing the energy of things around them. Because when you take a charge and accelerate it through an electric field, it gains kinetic energy. We can compare this to an object accelerating through a gravitational field, and this lets us compare force, energy, and potential. Remember, an electric field is defined by an electric force divided by a charge. So the amount of force felt by a charge divided by how big that charge is tells us the strength of the electric field. Now we also know that a force causes change in energy over some distance, and a change in energy is the amount of work done. So if we move a charge through an electric field, we are doing work. This introduces the idea of electric potential, or voltage. Electric potential is the change in electric potential energy divided by the charge. Another way to say that is that the electric potential is the electric potential energy per unit of charge. And if force is the change in potential energy over some distance, then we can extend that to describe an electric field as the change in electric potential over some distance. Suppose you have a 12-volt motorcycle battery that can move 5,000 coulombs of charge, and a 12-volt car battery that can move 60,000 coulombs of charge. How much energy does each one deliver? Well, a 12-volt battery means that it has a potential difference of 12 volts across its terminals. So when charge moves through the battery, the charge moves through a potential difference of 12 volts. We also know that the change in potential energy of that charge is equal to 12-volt potential difference times the magnitude of the charge. So the charge on the motorcycle battery is 5,000 coulombs. So the change in potential is 6 times 10 to the 4th joules. The car battery holds a charge of 60,000 coulombs and so has a change in potential of 7.2 times 10 to the 5th joules. Even if you have two batteries with the same potential difference, or voltage, they may not be able to supply the same amount of energy. Also note that when figuring the change in potential energy, we determine the absolute values. Since the battery is losing energy in this process, to be technical, we would want to say that the change in potential energy is negative, meaning that the potential energy of the battery decreased. Most electrical systems, including these batteries, are moving negative charges. In a battery, the negative charges are repelled away from the negative terminal towards the positive terminal, resulting in a positive potential difference from A to B. Taking a positive potential difference by a negative charge gives us a negative change in potential energy. So how many electrons pass through a 30-watt headlight each second if run by a 12-volt battery? Well, we're looking for charges moving through the headlight in 1 second. According to our equation, in order to find the charge, we need the change in potential energy and the change in potential difference. Potential difference was given at 12 volts. We also know the power of the headlight, and remember that power is joules per second, so we actually do know the amount of energy flowing through the light. Second, there is a change in potential energy of negative 30 joules. Once we know that, we can find the magnitude of the charge moving through the light as 2.50 coulombs. However, we are asked about the number of charges. If you remember from our discussion of static electricity, the charge on one electron is 1.60 times 10 to the negative 19th coulombs. So taking our total charge per second and dividing it by the charge of one electron, we can find that there's 1.56 times 10 to the 19th electrons flowing through the headlight each second. Now, electrons are tiny, and on the macroscopic level, the amount of energy they carry is tiny as well. At the atomic level, however, the amount of energy can be significant. So when we talk about the interactions on that level, it's convenient to define a different unit of energy so we don't have to deal with all those negative powers of 10. Enter the electron volt. Why not electron joule? Well, I have no idea, but an electron volt is the amount of energy produced when a charge is accelerated through potential difference of 1 volt. Now, this is just one charge going through 1 volt. What if we have a double charge? Well, we would have 2 electron volts. What if we move it through 12 volts of potential difference? Well, we would have 12 electron volts. So at the atomic level, electron volt is the energy unit most commonly used. And speaking of energy, guess what? Energy is conserved at this level as well. Just like in mechanical energy, the initial kinetic energy and initial potential energies will equal the final kinetic and final potential energies. We can calculate the final speed of a free electron accelerated from rest through a potential difference of 100 volts. Taking our expression for conservation of energy, we can substitute in what we know. The electron starts at rest, and we are going to convert all of its potential energy into kinetic energy. Initial potential energy is going to be the charge times the voltage, and kinetic energy is figured for an electron in the same way it is for larger objects. So we can solve for v squared and plug in what we know. This gives us the velocity of the electron as 5.93 times 10 to the 6th meters per second. Now, we discussed how the gravitational field does not have much of an effect on electrons, and by looking at how fast an electron can travel, that kind of helps support that claim.